Unsurprisingly to many, one of the most frequent things that you'll do in a functional language is define functions and use functions and do more advanced things like combine functions or things like that too. We'll start off with some simple definitions of functions to look at how they're defined, what their syntax is in Haskell, and how they can be used. So if we're in the interactive interpreter here, we can say let f of x equal x, and this gives us a very simple function, the identity function that just gives you back whatever you gave it. We can examine the type of f, which is it takes some type t object and gives you a some type t object back. We can define let g of x, where that equals x plus 1. And now the type is a little more constrained. It knows it needs to be some type of number. It doesn't really care what specific type of number, and that you're going to take that number type called a as an input, and you'll give out a result that is that same number type a. If we define h of x to be equal to x plus 1.0, then our type is even more restricted, because to add 1.0, then your result will be a fractional, and to add together, you need another fractional on the other side too. Here's a function called print third that takes something and prints out on a new line, or on its own line, the third element, the one at index 2 rather than indexes 0 or 1, from S. So Haskell will infer for this function that it takes a list of strings and that it results in IO, because that's what the put string line results in. If we call print third on a list with 3 different strings, excuse the missing quotes there, then we get out 3 printed. And we could redefine print third in a number of other ways, and I want to show you some examples of things that you can do. So we could do composition here, compose put string line with the indexing at index 2, and it will take S as a sort of implied input. So you see we have no parameter here, and that's okay, because what's defined here as a function is really just a name for some value. Functions are a type of value in Haskell, and this one has some remaining need for an input because we didn't say what we were indexing, and therefore it's gonna require that input to actually give us out a result. Remember that when we use the composition operator, what we're looking for is for the result of the right-hand side, the resulting type from the right-hand side, to be the input type of the left-hand side here. So Haskell will be able to infer that what's needed on the right-hand side is a list of strings, and that what's given here is a single string from that, and that single string will be printed using the put string line here. We could define the exact same basic thing using an anonymous function. Anonymous functions are a function that just doesn't get a name, therefore it's anonymous. We indicate only what their inputs are and what their process is to get whatever their output is going to be. So where there would be a name, we just do a slash, and then whatever our input should be called. So here we do /s, indicating that we need no name for it. Its input will be s, and then the arrow tells us that on the other side is what our actual process to derive our output will be, and our process is to do put string line on the result of s indexed at 2. and this will get named print third, and therefore it will be equivalent to the original definition, also equivalent to this second definition here. We can also just use the let statements to give different names to existing functions. So here we've just renamed tail to be called chop, and we say chop Haskell. It chops off the H, the first item from that string, which is also a list of characters. We can use that magic variable it that uses the result of the last statement and say chop again, and that will take off the A, chop again, and that will take off the S. So this will hopefully help you to cement in your mind the idea that functions are a type of value. They're just a special type of value that takes some input and gives some output, but that when we name a function, we really are naming some value, and that we may list parameters when it makes sense in the format that we're using to do so, but we don't necessarily have to. If we are saying that print third, for instance, is going to be the result of composing these two functions, then we don't need parameters for it because those functions already know that they need to take parameters. And likewise, we're just giving a name to this anonymous function here, and that's okay too. Or we're giving a name to this existing function of tail. Anonymous functions, by the way, will be extremely useful to you when you do things like folds, maps, things like that, because you could just put this in parentheses, and that could be the function that your map does with every item in some list. So you can define the function right there in the line as you're about to use it. Here's some other examples of defining functions. We can define an even function that takes a number n. In fact, it will be specifically limited to an integral in the way I've done it here because I've used mod, which has some limitations on its types. So here we've said if mod n with 2 as the base is equal to 0, then we return true, or we give true as our result, else we give false. Mod if, and here we simply just make the Boolean statement mod n2 equals 0, and we check even on a few different things. It's false for 5, it's true for 6. We can define odd now because we know even as the composition of not and even. We can't just say not even because that will attempt to apply not to the function even, but the input for not needs to be a Boolean. It won't know how to handle a function. When we compose, again, what we're saying is do even and feed its result to not. Even returns a bool, and so we can feed that bool to not and get our result. And now we see the outputs are reversed. Odd 5 is true, odd 6 is false. Here's a decrease or decrement function that only decrements if n is greater than 0. So then it will give n minus 1. Otherwise, it will give n. Here you can see that the type for that function is from A to A, where A is restricted to be a number and able to be ordered so that we can do that comparison there. And we can do these decrements on different numbers. Remember that in a purely functional language like Haskell, this does not change 4, or if I said decrement x, it does not change x. It applies decrement to x and gives us a new result from it. And here you can see that it doesn't decrement 0 and it doesn't decrement a negative number. Let's take a look at some more interesting ways that functions can take parameters. When a function takes a tuple or a list as a parameter, it can actually pull out pieces of that tuple or that list. So for instance, this one is called third. It's set up to be similar to the first and second functions that exist for tuples. Those are as far as you can go with those built-in functions. So here we've defined one that's called third. So it takes some tuple with x, y, and z, and it just returns z. Well, another interesting thing that functions can do is you can define them to take some parameters but ignore them. So this third doesn't have to give names to x and y. It just says something, something, and z, and I'll return z as my value or as my result. You can do this even with parameters that are not inside of a tuple. If you had two things and an empty list and you knew that you could return the empty list, well, you can just say blank blank empty list and that you're going to return the empty list. These will be useful for more advanced function definitions that we'll see later on in another video. So here we are using third on the tuple 5, 6, 7, and we get 7 out. But the problem is, again, with the strict typing of Haskell, the tuple 5, 6, 7, 8 is not of the type that is defined for third. The type that is defined for third is a tuple with 3 items. And so we can't apply a 4 tuple or a fortple, whatever, in third here. We could define a version of third that takes tuples of size 4, and it would work for this one, but it wouldn't work larger. We will eventually be able to see how to write much more generic functions than the ones that we're writing here, though tuples can particularly be a little tricky because their type is defined by their size, whereas a list, it's a lot easier to sort of split it out and say, I'll get the first item or 2 or 3 or whatever, and there will be the rest. So we'll see some examples with lists where we can be a little more flexible. Here's a definition for a function called swap that takes a tuple xy and gives out yx. So if we say to swap 1, 2, we get 2, 1. If we say to swap the result of swapping 1, 2, well, the inner swap turns it to 2, 1, and the outer swap turns it back to 1, 2. Here's a little more complicated one called swap 2. Now, the interesting thing about it is it appears at first glance to only take a tuple, just like swap does. And in a sense, it does. It takes a tuple, but what's done with them, with the items of that tuple, shows Haskell that you're actually talking about a tuple where each item from that tuple is itself a tuple. So A, because we've called swap A inside, we know swap takes a tuple. Therefore, A must be a tuple. So we see in the resulting type for swap 2 that T1 and T, this tuple here, is what we have inferred, what Haskell has inferred for that element A there, that it must be some tuple, and that tuple will be swapped, and that B must be some tuple as well, because swap was done on it, and that tuple will be swapped. So this is an interesting case of the inference taking what we've done and making some conclusions on what type of thing is being handed in here. You will see this happen a lot in your functions with lists, for example, where if you do list operations on B, say, inside of the actual function's body, then Haskell will infer that B must be a list. And so often, for instance, people will misuse the colon versus the plus plus, and Haskell will infer that one of their parameters was supposed to be a list when they didn't really mean it to be a list, because they used plus plus when they really meant to use colon, and it inferred that the thing on the one side of plus plus was a list. So you'll get mismatches in this way if what you do inside your function tells Haskell you're actually using a more complicated type than you intended to be. It's something to be very, very careful about, because what your function looks like and what its type is will not always be the same. Here is a function written for lists to get the third item from it. So it gets the tail of L, and then the tail of that, and then the head of that. So what that does essentially is it removes 2 items and then gives us the head of the remaining list there, the third item. Not index 3, but index 2, similar to our one that was dealing with thirds before. So the type of list third is that it takes a list of something. We don't really care what type it is, and it gives us one of those somethings. Here is a function called dig, which takes a list also, but it takes a list of lists. So this is another of those examples where L looks like a single type of parameter. It looks very simple to look at this function. But if you're asking for the head of something, you're actually asking for L to be a list of lists of lists. So often, programmers who are beginning in a functional language will do something like this. You're trying to get the third, for instance, from a list. And so you'd say head, similar to how in a linked list in many programming languages, you would say like head.next.next or something like that. Many people try to apply this logic. But when you call head, Haskell will infer that L is a list. Then when you call head on the result of that, Haskell will infer that what you got from that other head call must have still been some type of list, so L must have been a list of lists. And then you call head again, and it says, well, the result from that second head must have been a list as well, and therefore L must be a list of lists in order for head to be meaningful 3 times. There has to be sort of a depth of 3 to it to dig down into a list of lists like that. So if that's what you're aiming to do, like this one shown here, that's great. That's fine. If that's not what you're aiming to do, you need to be very careful about your use of things like head versus tail. Tail returns a list, but head does not typically, unless you have a list of lists. Here is a function called first3 that takes a list. It will get the head of the list, the head of the tail of the list, also known as index 1, and the head of the tail of the list, similar to what we did up here, which would be index 2. And so if we give it 4, 5, 6, 7, 8 as a list, it will give us 4, 5, 6 as a result. Versus this call here, if we call with a list that's too small, then it's interesting to note we don't get an error about types, because the type of first3 is a function that takes a list and gives out a list. Well, that would be possible. This is a list. And so tuples are defined with their type as their size. Lists are not. You'll notice none of these lists show multiple elements, even though we're doing stuff sometimes that involve multiple elements. When you look at the type of the functions, it looks like the list only has one thing in it, because really what it's saying is this is the type, and it could be any amount of it, versus the tuples, which when we looked at the types for them had specific lengths defined for them. This one similarly would have had a specific length of 3 items defined for it. None of our lists will. So you will not get an error at the time of writing your function. If you do something like this, you will get an error at runtime when you try to execute your function on 4, 5, and it will try to get the head of the tail, where the tail of the tail would be too far down. You would not have a head left to be able to get information from it. It would be an empty list. because the tail of this once would be just 5 as a list, and then the tail of that would be an empty list. So we're not able to finish executing there, but it is not a type-based error in this case. Let's take some time to look at writing recursive functions because, well, we're going to do a lot of it. So here's the pretty classic example of factorial. Factorial of n. Well, if n is 0, then our result is 1. Else, we result in n times the factorial of n minus 1. That should be hopefully pretty familiar to you. And we can do factorial of 10, and it seems to work just fine. The type for factorial is defined to be from a to a, where a is a number, and it's a number that equality can be done on it because we've done some equality checks here. Here's a list-based recursive function. It says it will get the first n items, so you define some n for it and a list, and if n is 0, it gives you the empty list. Otherwise, it gives you the head of that list combined with the result of first n on n minus 1 and the tail of the list. So it's just going to grab the first thing and combine it with the recursive call on n minus 1 and the tail of the list. And it works just fine for giving it 4, and we get 1, 2, 3, 4 as a list from it. We can also write an append that takes two lists and will append them to each other, similar to plus plus, the built-in operator. If list 1 is empty, then we give list 2 as our result. So this is our base case. Once we've passed all the stuff in list 1, then we know that list 2 is going to be combined on with all the stuff that we grabbed there. What we're doing in the recursive case is we're grabbing the head of list 1, and then we're calling append on the tail of list 1 and list 2. So this would, for instance, call with 1, 2, 3, and 4, 5, 6, which would grab 1 as the head part, and then 2, 3 would be the tail part that the recursive call is done on. Then it would call recursively, it would grab 2 as the head part, and 3 would be the tail portion that the recursive call was done on. Then it would have 3 as the head and the empty list to the recursive call, which would put us into our base case where list 1 is the empty list. That's when null, the function null, tests lists to see if they're empty, and so it would return true, so we would return just list 2. So the recursive call here would be list 2 combined with 3, and then it would come back up the stack. The list 2 plus the 3 combined with 2 that was the head, combined then with 1, and it gives us that full list that we've created here. 1, 2, 3, 4, 5, 6. The type of append is pretty simple. It takes a list of anything and another list of anything, and it gives us out a list of anythings. And last we'll look at this nth, which is really just an indexing sort of function. If n is 0, then we give the head of our list. Otherwise, we call nth on the tail of our list with n minus 1. Pretty similar to our first n up here, but it doesn't combine the result into a list. It just gives us out whatever the item was at that index. Now, many of these are not particularly secure, and we will actually see better ways to write. By secure, I mean they will not handle bad input very well. This one, for instance, would not handle well if it was a negative input, and it will not handle well if it's an index that's out of bounds. And sometimes we might leave that, but there are also better methods that we'll see when we get further into digging into functions for defining functions and making sure that they handle lots of different cases. We could nest our ifs and have some sort of if n is less than 0, then we'll do something, then else, etc. and then have an if nested inside. We can do those. There will be cleaner ways to handle a wider range of cases for functions. But for now, we can see the limitations of some of these. This one would not handle negatives very well, or ones where the index is out of bounds. This one would not handle negatives as well, particularly well. Neither would our factorial. So we'll see more advanced methods. I'm not going to dig into really well-defined versions of each of these because we'll see better methods for handling more advanced functions that need lots of possible cases to handle. Here's a concatenate function. If we're given the empty list, then we return the empty list. Otherwise, we append the head of L and we call append on the head of L and the result of recursively calling concat on the tail of L. So what this is doing is it's taking lists of lists and combining them into one single list. So it would take the 1, 2, that's your head of L, getting called with the append. It's taking that head and appending it with the result from concatenating all the others. So its type is a list of lists of t's to a list of t's. Here's something worth noting just to remind you of a concept. So there are good and bad ways to write recursive functions. We'll see that in Haskell in particular, there are kind of extra bad ways, and that neither of the examples I show here is particularly Haskell-specific good. That's why they are called bad and better, but not necessarily good. But a bad way to write a reverse function recursively would be to say, if you have the empty list, then return the empty list. Otherwise, recursively build up this sort of chain of taking the tail and combining it with the head, and it would do this, it would call this over and over, never be able to actually do the combination until it returns from the last one where it has an empty list. Then it's able to give the empty list and combine that with other things. By the way, this is bad rev getting called on the tail, and that result will be combined with the list that contains only the head. So we have to get this result from bad rev to be able to combine with the head. So we have to call all the way down before we can do any of the list building. Often a better way to design things is tail recursively, where we build up some accumulated result and we call recursively adding to that accumulated result with less of our list or less of our data to have to deal with. So here we just define better rev on a list to be calling that G, that tail recursive helper, using the empty list as the starting accumulator and L as the actual input to it. This one can be much faster. There are still some optimization considerations we would want to take into account for this function in Haskell in particular, but it is tail recursive, and that gives us a little more advantage, being able to start to build the list before we get all the way down to the end. We build up the list as we go, and then we get down to the end. So the bad rev here will be very, very slow because it can't do any of its work until it's gotten all the way down to the end, and we can get big memory usage and possibly stack overflows for larger lists when we do these. Because functions can get so big and you might want to reuse them, I'll talk about a few different ways that we can get functions, such as libraries, and I'll also talk about ways that we can sort of hold on to our own functions in files and bring those in to either the command line interpreter or into other code that we want to reuse some of our functions in. So some of the built-in libraries that are very helpful, for instance, are data.list, where you get a variety of additional list functions that can be very helpful in processing or doing things with lists. Here are just a few examples. By the way, if you're in the command line interpreter and you want this, you type import data.list and you see that it sort of adds it to what you've got loaded. It will show you what things you've got loaded in. And we'll see in a file how to do something like that too in a moment. It will involve just import as well. So here we can concatenate, or we can use the built-in concatenate method that will take, concatenate function that will take a list of lists and give you out a single list. Here's an interesting one called intersperse, which will take some list, like a string, which is a list of characters, and insert some item in between every item from the original list. So here we're inserting a star in between each of the items. And there's the AND function in that list library, which will apply, or it will check that logical AND against all of the items in the list. We could write a similar thing using folds if we wanted to, but why would we when there's a nice built-in one? Data.character here is a useful library as well that we can load in. It gives us lots of things to check information about characters. Is something a space? Is something alphabetical? Is it uppercase? Is it lowercase? We can transform things from uppercase to lowercase. We can even map these character functions onto strings, since strings are lists of characters. So here we're mapping is alpha to see, is everything in this string alphabetical characters? Now we talk a lot about map as a behavior and as a function in functional languages, but of course many of you are familiar with map as a data structure as well. So here's an example of importing the data.map library. It's worth noting that you can kind of shorten the name or give a nickname to something by using qualified, and then you can name it as map, for instance, here, so I don't have to type out data.map lots of times or things like that. So this allows me to do things like say, let's create a map from a list. It will have to be a list of tuples where one is the key and the other is the value. So this creates a map from the list Sophia teacher and will let us store that as M and use that name M. Map.empty is just a shorthand for an empty map with no keys or values. Here we're seeing the result of M, and it's showing us that it's really essentially a list with Sophia and teacher as a tuple, but that it's going to be treated as a map. We can use the function map.insert and give it a key and a value as long as those types match what we expect as keys and values, and we tell it what map we're wanting to insert into. Now, the tricky part is, again, this is a functional language, a purely functional language. When I say map.insert John Machinist M, that does not change M. That gives us a result that is a new map that now has both John and Sophia as keys, but it did not change M. The original map is still there. So if we wanted to hold on to this, then we would need to store it or use a variable name for it, like a let M2 equals that, or use it in a function in a way that actually is meaningful for us as well. And most often that's the sort of thing we'll do. You'll want to try to create a million variables, but the better way to do it is to use it inside of a function somehow. Map.lookup will look up the key and give us out the value. It's worth noting that this uses the optional type that's called actually maybe, capital M, maybe, which can either be nothing, because nothing was found, for instance, or it's labeled as just and then some actual value. This is different than the string teacher because this is in a special type that's allowed to be nothing. You can use maybe types for any kind of value. They're not specific to maps, but this is a useful case to introduce the idea because with maps, we need something to be done when we do a lookup and we get no result. There's not a null or something like that, and it would be very confusing in Haskell to have a null for every single specific type. So instead what we do is we have this sort of wrapper type of a maybe, and a maybe can be nothing or it can be just and then a value. When you're writing your own functions and using your own values in Haskell, it's often going to reach a point at which you need to store those in a file. And you may even want to group them in a way, say you're doing one of the homeworks, and you group some of the functions or some of the functionality in one file, and you group some in a different file, and you might want to bring them together into some main file. Well, here's a brief example of how you can do that. Here's a module called helper. It's defined in helper.hs. Capital letters are required for module names. So it's strongly advised that you use modules when you're grouping together some functions. For your homeworks in this class, you'll have to use a module for each of those so that they can be loaded in easily into other files. So here we've created the module helper, and then we say where, and it gives all of the function or variable names that we're going to use through here. So we've defined pi, we've defined a function called degree to radian, which uses pi to turn things like 90 degrees into radians or stuff like that. We've defined a square function, which does x times x for some x, and we defined a cube function, which does x times x times x. And then we can use those down here in main.hs. We import helper, and then we can define our own new stuff. You can also use main equals as your statement inside of a Haskell file to define what would happen if you ran that program as well. So we could say main equals, to print out some results from our program here or things like that, or get input from the user and do some of our math with that input. So here what we've done is we've defined some new things. C equals cube pi and D equals degree to radian 90. And then we defined a new function using some of those functions that were defined in helper. We don't need anything before those function names when we import like this. They just come in similar to if they were declared inside of this file. It's also worth noting that inside of a file, we don't have to type let everywhere. In fact, inside of our files, we'll see a different use for let because we can use it inside of structures like functions or things like that. Whereas at the command line, the interpreter, GHCI, we had to use let when we were defining stuff. In our files, we won't have to use let, so we don't have to say let square x equal x times x. But if we wanted to try this in the interpreter and just sort of copy and paste it in there, we would have to add a let before it in that case. Speaking of the interpreter, we can open the interpreter and we can load in the files that we have created. So for instance, if we ran the command hgci main.hs, you can see here that it compiles and loads in helper, and it compiles and loads in main. By the way, it is the default that you actually are creating a module when you create any Haskell file, and the default name is main with a capital M. So you'll see that it reports itself as if it were running in some module called main here. So we can use degree to radian with 360, and we get this value, 6.28 something. We can define things. Here we again have to say let to define them. And we define A to be degree to radian 45. And we see what A's value is here when we ask for it. We can call norm 1 and 1, and we get a new value out of it. We can check on the type of some of those different functions. This might be useful to you when you're testing out your programs to make sure that you've actually specified the functions that you were supposed to specify or that you thought you were specifying, in terms of does it take a list when you thought it was not taking a list, or things like that. And we can see some more of the uses of those functions and those values here. We can use them in more complicated expressions as well, like checking whether d is equal to half of pi, which it is. So here we've seen some basics of defining and using functions, how their types are established and what their types might look like. Some more on recursive functions and a tiny bit about making them good, but we will approach that more later. And then some about getting functions in, either from built-in libraries or from your own files. So I hope that this opens up to you some more opportunities to try some things out in Haskell and gets you a little more ready to move forward into some more interesting ways to define functions and to make well-performing sort of code in Haskell in the future.